Yesterday you guys were starting on the lab on impulse and momentum. Remember, impulse is force times change in time, or Ft. And really, if you think about what I'm saying is, this is the duration of time that a force acts times however big the force is. Okay? And we learned that that is equal to the change in momentum of an object. Now, I mean, that's just Newton's second law. Net force equals mass times acceleration, and acceleration is really just change in velocity over change in time, right? And so if I replace that in this equation, I have net force equals mass times delta V over delta T, and if I multiply both sides by the delta T, then net force times delta T equals mass times change in velocity, and that is change in momentum. Alright, so enough of that. Let's talk a little bit about a couple of those questions. The pre-lab questions, there was like, hey, if you're in a car and you got to go from moving to not moving, so what difference does it make if your face smashes directly into the steering wheel or into an airbag first? This is supposed to be an airbag, okay? There's a face, okay? How is it better to smash into an airbag than it is to smash into a steering wheel if you just got to come to stop anyways, okay? Well, the biggest difference is, okay, when you hit an airbag, you're going to slow down over this entire distance. Yeah, granted, it's going to take still a pretty quick amount of time, but you are going to slow down over a greater distance. If you just smash into the steering wheel, okay, the distance, there isn't really any, okay? And so it takes a more amount of time for this to happen, so delta t is greater than the delta t over here. And if we think about what that means, right, your change in momentum has to be the same because you're going from some initial velocity, v naught, whatever it is, to some final velocity, 0. Okay? It's the same in both cases. You're going from moving to not moving. This one takes greater amount of time, which means less force is necessary. Okay? So if you think about this, since net force times time is equal to change in momentum, there's a couple different ways we can alter something. Okay? You can use a really big force over a very short amount of time and get a pretty big change in momentum. And generally that's what happens in a collision, right? The forces are nothing and then the objects smash together and you get this big giant peak of force. Okay? So this is force, this is time, and this right here, this is that force that acts over a short period of time and it causes a really big change in momentum. Or you could say, well, what if we started the force a little bit sooner, didn't let it get quite as big, and made it go a little bit longer? Okay? Then we have not near as big as force, but it acts over a much longer time. These two things could produce the same change in momentum, and as long as the masses are equal, that's the same change in velocity. Okay? So the impulse momentum theorem explains a lot of things. Why do we use bumpers on cars? What's the purpose of the crumple zone? Why do we have the airbags? They're all designed to make the force last for a longer amount of time, which means that less force is required in order to get something to stop. Okay. Now I'm going to assign a few problems today to work over impulse momentum, as well as I want you to finish that lab. So let's see. In your book, I'm going to work a problem here real quick. It says a 2,200 kilogram car traveling at 94 kilometers per hour. So I got a mass of 2,200 kilograms. Is traveling at a speed of 26 meters per second, which is 94 kilometers per hour. Okay, and it can be stopped in 21 seconds if we apply the brakes. It can also be stopped in 3.8 seconds. Okay, so 21 seconds with brakes, 3.8 seconds if this is gently applying the brakes, coming to a stop. 3.8 seconds if you slam on the brakes, okay, and you're trying to avoid something. Or it can be stopped in 0.22 seconds if you hit a wall. Okay. Granted, hitting a wall is not generally the best option to stop, although when you ice skate like me, it is sometimes your only option to stop. Okay, so what average force is exerted on the vehicle in all of these stops? Okay, well, to figure that out, okay, let's figure out the change in momentum. Okay, the change in momentum for every single one of these cases is going to be the same because they all start with a v0 of 26 meters per second and they all end with the same final velocity, 0 meters per second. So my change in momentum is equal to mass times change in velocity, which is mass times 0 minus 26, or 2200 times negative 26. That's the change in momentum of the car. So it doesn't matter how long it takes for the car to slow down and stop. As long as it's going from the same initial speed to the same final speed, its change in momentum is always going to be the same. And for this particular one, that is $57,200. Okay, now what's my unit here? Okay, this was kilograms. This was meters per second because that was my velocity. So this is kilogram meters per second. And it is technically negative. It does make sense to talk about a negative momentum change, right? If it was initially moving this way and now it's stopped, that means the force had to act that way. The acceleration was that way. So yes, it is a negative change in momentum. That's okay. Now, it says what average force was required in all three of these cases. Okay. Well, you guys can look at this and see if you take 21 seconds to slow down and stop, it doesn't take much force, but it does have to act for a long time. You slam on your brakes, yeah, it takes a lot of force. That's why when you come to a nice gentle stop at a stop sign, you don't hardly feel it. But when you have to slam on your brakes to avoid hitting something, everybody feels like they fly forward in the car. And then if you hit a wall, don't hit a wall. Okay, so let's go ahead and figure out what we're going to do. Okay, we have Newton's second law, which is net force equals mass times acceleration, but then I have to find the acceleration for all these cases. Or I have Newton's second law, which is net force times time, change in time, equals change in momentum. So now my change in momentum is always the same, negative 57,200 kilogram meters per second. That was one extra zero. And so the force is always just equal to this change in momentum divided by time. So for case A, 57,200 divided by 21, we get 2,724 newtons. Okay. For case 2, where you have a shorter time, 57,200 divided by 3.8 seconds, okay, it's considerably more force. It's 15,052.6 newtons. Okay, but for case 3, where this thing hits a wall, 57,200 divided by 0.22, right? That's basically, say, multiply your force by 5. We get 260,000 newtons of force. Okay, that's a lot of force. And since your body is going to undergo the same force that the car undergoes, essentially, that's going to cause you to accelerate. So 2,700 newtons of force, that's a lot of force to stop a car. It causes the car to accelerate. Okay, but that's not a whole heck of a lot going on. Just by slowing down how much time it takes, or I guess speeding up how much time it takes, I don't know how you'd say that. Okay, we're going to go 100 times more force. Okay, from 2,700 newtons to 260,000 newtons. Okay, this is why bungee jumpers use stretchy cords, right? You don't want your rope to snap. You want your rope to slowly slow you down over a long distance of time. Otherwise, if it's a short stop at the end, right, quick jerk, not good for you. Okay, so the impulse momentum theorem just says, hey, if we can use the force over a longer time, then we don't need quite as much force. Okay, I want you guys to work on page 233, numbers 1 through 5, and on page 235, numbers 6 through 10 and 12. You do not have to do number 11. Let me know if you have any questions, and if you need to finish up that lab, you can do that first.